My name is Glauber. I'm working at DigitalOcean in the kernel and performance team, and I would like to briefly talk about what we are doing for I/O latency monitoring. So we are a cloud provider. We do have a fleet of servers with lots of VMs running QEMU and KVM, and we need to continuously monitor performance data for internal and external use. We do get a lot of metrics per virtual machine for CPU, memory, I/O network, and much more. And we use Prometheus and Grafana to store and retrieve the data. One area where we wanted to improve ourselves was measuring of local storage. We only had per disk latency per machine, so we didn't have any per VM data. We didn't have data for read-write operations, and also latency is influenced by many factors, for instance, by block size or by number of I/O operations. So basically, we wanted to monitor and track every single I/O request. That's where eBPF came into play. It was already used heavily for tracing, so I thought it would be a good match. Now we had a number of questions at the beginning. One thing is we have a complex disk setup with RAID, DM, LVM. So which layer should we trace on? Should we trace requests or block IOs? Luckily, there are trace points already in the IO path. So should we use trace points or raw trace points, or rather stick to K-probes? Also for user space tooling, we are bound to Golang because of our middleware stack. So we needed to decide which library to use where. And also, what's the performance overhead of eBPF? What would it mean? We already knew that we couldn't monitor every single I/O event, but had to kind of aggregate inside the kernel. So I played around with different options we had and finally decided on using raw trace points on block I/O layer. That was good for us because tracing the block I/O struct, we can do a lot of filtering. So I filter out every disk I'm not interested in. We can filter out processes we are not interested in. So this is a short snippet of the trace points we are using. The actual code is quite longer. And with this in place, it was quite easy to implement the whole thing. So at the bottom, we have the VMs. And as we have the I/O path instrumented, whenever a VM does I/O, we atomically increase the counters we are interested in. The counters you can see in the eBPF maps part for read and write operations, for bandwidth and IOPS and other things. And we're the simple hash map indexed by the process PID. And then on the left side, we do have a user space component that tracks all the active VMs. From time to time, it gathers the data from the eBPF hash tables. And it also has to do householding because VMs come and go. So from time to time, we need to remove inactive VMs to not fully utilize the eBPF maps. And then we can create histograms or P90 or whatever from the data we have and export it on a local port so it can be retrieved. So to summarize, as I already said, we do tracing on block I/O layer. We use raw trace points. We decided to use Cilium eBPF, which worked greatly. We measured that the performance overhead is quite low using eBPF stats. We do have a possibility for custom filters, and it's easy to extend the eBPF code. And it's also faster than parsing procfs. So what's open? Every project's got a to-do list. And the biggest pain point for us is kernel versioning support currently. We had to ship multiple eBPF programs matching the kernel versions we are using. So that's something we need to work on. Another thing is we had to extend eBPF code to have kind of versioning between our user space component and eBPF because the data structures can differ. We need to make sure it works even after an upgrade. And there's more to do, like dynamic map sizing, which we didn't yet look into. So thanks for your attention. I would love to hear your feedback or comments.